Okay, so welcome back, everyone. We're in for the third and last hour of this crash course. By the way, I'm not sure why they call it a crash course because it sounds very ominous, but we've covered a lot of material, and if you feel like you're sort of keeping up, we're basically cramming in like 5 weeks of introductory quantum computing course. If you're sort of partially following along, then that's really good. Before I start into this advanced quantum information theory, let me just quickly say one or two more things about the Grover search algorithm that some people brought up in the chat. So I described how Grover's search algorithm works in the case that there's you're promised that there's one solution, f of x equals to 1. But what happens if there are a different number of solutions? Well, if there are no solutions, then Grover's algorithm will never tell you that there is a solution. So that's one thing. Well, what if there are more than one solution? What if there's in general t solutions? Then actually the number of queries, and let's say you knew t beforehand, or you had some estimate, then actually you can make fewer queries than square root 2 to the n. In fact, you can make square root 2 to the n divided by t queries. What's even more remarkable is that even if t is unknown, then using a slightly more clever algorithm, but using a lot of the same ideas, you can still find a solution in expected number of square root 2 to the n over t queries. Okay, so that's some nice things to know about the Grover search algorithm. So, okay, let's turn to advanced quantum information theory. And now we're going to talk about something called mixed states. So, up till now, the way we've described quantum states are through, they're unit vectors in c to the d. We call these pure states. And the reason we call them pure states is because if we have a quantum state and we say we know that we describe this state, the system using a unit vector psi, then essentially the state of the system is determined. And what we mean by that is essentially we know everything there is to know about what this state is. Even though when you measure, you might get a probabilistic outcome. But if you don't measure it and you apply unitary transformations, we know exactly what the outcomes are. Another way of saying it is that given a pure state, if a system is in a pure state, there is some basis that you can measure in which the outcome will be, there will be a probability 1 outcome. Okay, so that's what what I mean by determined. But let's say that someone behind their back flips a coin, and depending on the outcome of the coin, hands you either the 0 state or the plus state, depending on the coin. And they give you this quantum state, but you don't know what the coin is. So the only way to describe the quantum state that they gave you is through something called a mixed state. And we say that it's a probabilistic mixture of, say, 1/2 probability 0 and 1/2 probability the plus state. What's important is that this is different from saying the equal superposition of 0 and plus, right? That is a different thing. That would be a pure state. But here we're saying that it's a probabilistic mixture. And in order to mathematically describe this mixture, we use something called the density matrix formalism. Okay, so now we're going to make this switch, this change of formalism, where instead of describing states by vectors, we're going to describe them by matrices. And it turns out that this way is sort of the right way to think about when we have a probabilistic mixture. So formally speaking, a density matrix is let's say you have a d-dimensional system. A d-dimensional density matrix is going to be a matrix rho that's positive semi-definite, which means that all of its eigenvalues, it's a Hermitian matrix, and all of its eigenvalues are non-negative. And the trace of this matrix is equal to 1. So the trace of a matrix is you just sum up all the diagonal entries. Right, and the trace is a linear operation. Okay, so hopefully you remember that from linear algebra. Density matrices are the correct way to describe mixed states. So, so let's say you had a simple mixed state, which was, I gave you a pure state with probability 1. So this pure state psi corresponds to the rank 1 outer product ket psi bra psi. So this is it's an outer product, so it's a matrix. This actually is a projection matrix. So it's positive semi-definite. And the trace is indeed 1, right? If you take the trace of this, this matrix, it's 1. So it's a density matrix. More generally, let's say I have a probabilistic mixture of pure states psi 1 up to psi k, each of them occurring with some probability, you know, p1 up to pk. We can package this together into this matrix by summing over outer products of the psi i's weighted by the probabilities that they occur with, right? So again, you can verify that this is a density matrix, because if we, you know, it's a sum of rank 1 outer products, so it's positive semi-definite, and the trace turns out to be 1. So just to quickly show you, how do you take the trace of this thing? Well, the trace is a linear operation, so I can bring in the trace. So this is the probability, you know, the pi times the trace of psi I, but this is just equal to 1. And then if you sum up the probabilities, you get 1. So this is a valid density matrix. Let me just write some quick examples. So let's say we have these pure states 0 and 1, right? As we saw, these correspond to density matrices 0, 0 and 1, 1. If we were to write them in matrix form, this looks like 1, 0, 0, 0, and this looks like 0, 0, 0, 1. Okay, these are pure states. If we have a probabilistic mixture, let's say, you know, we had this 1/2 probability 0 and 1/2 probability plus, well, we can sum up these two outer products, right? And so we get, as in the matrix form, we get 1, 0, 0, 0 plus, I think we have 1/4, 1, 1, 1, 1, if you sort of write everything out. And then we should get, what is it, 3/4, 1/4, 1/4, and 1/4. Okay, so you can check that this is a density matrix. So basically in this story where someone flips a coin and hands you one of these two states, the way to describe the physical state of the system that's handed to you from your point of view, because you don't know their coin flip, it's this matrix. Let me talk about two examples that might seem a little different, but we'll see that they're actually the same. So in this first example, it's just a coin flip, 1/2 probability the 0 state, 1/2 probability the 1 state. So as a density matrix, this is the following sum. If I write it out in matrix form, this is 1/2, 0, 0, 1/2. This is just 1/2 times the identity matrix. This density matrix for a qubit has a very special name. It's called the maximally mixed state. And it just corresponds to a coin flip. Okay, so that's that's this density matrix. What if we take 1/2 probability the plus state and 1/2 probability the minus state, right? So it looks like we've done a change of basis, but let's see what density matrix we get out. So this is 1/2 outer product of the plus state plus 1/2 outer product of the minus state. You know, and you can sort of write out what these matrices are. This is, right, we already saw what this is. This is 1, 1, 1, 1 plus 1/4, 1 minus 1 minus 1, 1. But hey, when you sum this up, you get exactly the same matrix out, right? Again, this maximally mixed state, the identity over 2. So what is that telling you? I mean, it looks like you have two different situations. One is in the standard, you know, standard basis, and one is in this diagonal basis. But if you don't know the outcome of the coin flip, you get the exact same density matrix out. And what this tells you is that you cannot tell the difference between these two mixtures. Okay, so let's take a little aside. Let's take a segue. Let me briefly talk about projective measurements, just because you know, it's something that's useful. So we talked about measurements according to an orthonormal basis. There's kind of a slightly more general way of describing measurements, which is through projections. So if I walk up with a set of matrices M1 up to MK, they describe a K outcome projective measurement. If each of these matrices are projectors, meaning that they're, you know, they're Hermitian projectors, meaning that if you take their Hermitian transpose, you get the same matrix again. And if you square them, it's still the same matrix. So it's a projection matrix. And if you sum them all up, you get the identity. Okay. And you know, what's the rule with if you have such a projective measurement? What happens when you measure a state, let's say a pure state? Well, you obtain outcome I with probability that is, well, you apply the projection matrix to your vector. You get a projected vector, and then you take the length squared. That's going to be the probability. And then you just renormalize. That's your post-measurement state. Okay, and this sort of encapsulates what we talked about before. If you had an orthonormal basis, let's say B0 up to BD minus 1, if you take the outer products of these basis vectors, you get exactly the projective measurement operators. Okay, and you can see that this defining it, the M's this way matches up with all the rules with how we talked about measuring in a different basis before. Okay, so that's projective measurements. Let's go back to density matrices. Density matrices encode everything that is physically relevant about a probabilistic mixture of pure states. So I said that, you know, we have these two situations. One, you know, a random standard basis vector versus a random diagonal basis vector. They turn out to be the same density matrix. And since the matrices are the same, it means that no matter what operation you perform on this mixture, you know, maybe you do some quantum computation, you know, or whatever, you'll never be able to tell the difference. So that's why we package them into these matrices. Here's some rules about how these, you know, we talk about these density matrices. We can talk about unitary evolution. So if you have a unitary acting on, let's say, a qubit that's in a mixed state, the way we update the description of the mixed state is we conjugate the density matrix by this unitary U, right? So we have to put it on both sides. And, you know, if you're kind of weirded out by the fact that U appears twice, just think about the case that, you know, rho is just a pure state. So if the pure state gets updated to U times psi, as we're used to, then, you know, the mixed state corresponding to the updated state will be U psi, and then you take its Hermitian conjugate. Right? So that should make sense. What about measurements? So let's say we have some K outcome projective measurement. All right. If you want to measure, you want to say, well, what are the statistics? What are the probability distributions of the outcomes that I get from measuring this mixture? Well, you multiply your projection matrix Mi times your density matrix rho, and then you take the trace. So when this is matrix multiplication. So this is going to be a new matrix. And then you take the trace of that matrix to find out the probability. And it turns out that it will always be a non-negative number, and it will sum up to 1. Right? So one way to see that it sums up to 1 is what are the sums of these probabilities? The trace is linear, so this is equal to the trace of the sum of the mi's times rho. But since mi's form a measurement, this is trace of identity times rho, which is equal to 1. Okay. And this formula tells you how to compute the post-measurement state. Right, but we won't need this for now, but just so you have it for later reference. So those are the rules. We have unitary evolution. We now know how to take measurements. Let's again just consider a couple examples, just so we see this in action. Let's say we have a pure state. A qubit psi equals alpha ket 0 plus beta ket 1. We formed the density matrix corresponding to it, and let's measure in the standard basis. So the projective measurement corresponding to this would just be the outer products of 0 with itself and outer product of 1 with itself. So let's see what happens. Well, if we take the outer product as a matrix, this is equal to norm alpha squared times zeros, outer product 0, 0 plus alpha beta conjugate 0, 1 plus beta alpha conjugate 1, 0 plus norm beta squared 1, 1. So that's the density matrix corresponding to the pure state. And now we can compute the probability of, let's say, the 0 outcome. This is you take the trace of 0, 0 times psi, all right? And I won't go through the algebra here, but if you multiply these matrices together and take the trace, you'll get norm alpha squared, as you should, right? And similarly with the 1 outcome, you're going to get beta squared. All right. So we see that at least the rules for how you take measurements with density matrices coincide in the pure state case with what we've learned before. Okay, so that's one example. Let's consider this other example. Let's say you have this maximally mixed qubit, right? This identity over 2. And then we decided to measure with some arbitrary basis B0, B1, right? What are the probabilities of the different outcomes? And just to, in your mind, you can imagine that maybe the way that this mixed state was generated was someone flipped a coin and created a state in the, say the standard basis, picked a random, picked 0 with probability half or 1 with probability half, and they hand it to you. And you measured in this weird basis B. So the probability of the B0 outcome is, well, what's the rule? We take the trace of the outer product of B0, right? That's the projector corresponding to this outcome, times this density matrix, which is I over 2. Well, the identity matrix leaves this outer product the same. So this is 1/2 trace of B0, B0, which is 1. And so this is just equal to 1/2. And the same thing with the B1 outcome, right? You do the calculation, you're going to get probability half. So this tells you that no matter how this maximally mixed qubit was prepared, whether they picked a random standard basis state or a random diagonal state, And no matter what basis you measure in, you're always going to get a 50-50 outcome. So you can start to see why this it didn't really matter how this maximally mixed state was prepared. The fact that it's identity over 2 tells you everything you need to know. It just looks random. Okay, so let's start to see how this comes into play in a cryptographic setting. So let's talk about the quantum one-time pad. This is the quantum analog of the classical one-time pad, which we all know, right? So that the classical one-time pad says, let's say you fix a message M, and it's n bits long, and then suppose that you picked a uniformly random string S. Then the marginal distribution of the bitwise XOR of the message M XOR S is going to look like a uniformly random string. So you have no information about what M is if you don't know what S is. So you've randomized the classical information. So here's the quantum analog. It's called the quantum one-time pad. And let's just talk about it for qubits, but you can easily extend this to multiple qubits. Let's say you have a qubit state psi. We're going to sample not just 1 bit to randomize it, but 2 bits. We call these A and B. And we're going to apply z to the A, x to the B to psi. Right? So z to the A is, if A is 0, then this is just identity. Otherwise, it's z. Right, so there's 4 possible combinations, and it looks a lot like the teleportation protocol. Which combination of x's and z's and identity we apply. So we apply them. Then the claim is that if you take the mixture of these 4 possibilities, this is going to look like a uniformly random qubit. And what do I mean by that? If you calculate the density matrix, no matter what qubit psi you started with, the resulting density matrix is going to be this maximally mixed state. Right? As long as, if you don't know what these bits A and B are, right? So these are often called the quantum one-time pad keys, then the qubit looks completely random. So if you hand it to someone, they try to measure it, they try to do some computation on it, it's just like might as well just be a 50-50 coin flip. Okay, so this density matrix formalism is really useful, especially in the cryptographic setting when someone holds the keys, but you don't have it, you don't have access to it. So from your point of view, this mixture of quantum states could be the maximum mixed state, and it looks completely random. And it tells you that you can't extract any information from it. Okay, so let's talk about composite systems. Like just before, we had let's say single qubits. What happens if we want to talk about multiple qubits? Well, again, we use the tensor product. So if you have 2 quantum systems, one that's described by a mixed state rho, and the other that's described by a mixed state theta, then we can put them together. And okay, so here things start to become subtle. Let's say that these 2 systems are independent for now in a way that I'll describe later. Then we can describe their joint system by a density matrix rho tensor sigma, which is another density matrix. So let me write that down. 2. So these have to be independent systems. Okay, so we can build up larger systems this way just by putting density matrices together, by tensoring them. If you have n copies, then you can take n tensor copies, and it's often written this way, let's say rho tensor n. Basically you can think of rho tensor n, like let's say rho is the maximally mixed state. if you take n independent copies of the maximum mixed state, you get, it's like n coin flips. Then rho tensor n is equal to the identity of dimension 2 to the n. Yeah, so let me write it this way, divided by 2 to the n. So this is okay, and it just looks like n independent coin flips. Okay, but maybe not surprising, not all density matrices on multiple qubits can be written as a tensor product of individual density matrices on individual subsystems, right? But here things start to get subtle, because just because you have a density matrix, let's say rho on 2 qubits, so let's say we have rho AB, and we write AB to sort of indicate that this density matrix is on 2 qubits A and B, right? So this is a 2 qubit density matrix. Just because it can't be written as some sigma tensor tau, it doesn't mean that rho is entangled. And that's because these density matrices also allow you to capture classical correlations, right? So here I've written an example of a density matrix. It's 1/2 0 0 plus 1/2 1 1, right? In this state it just looks like I've either flipped 2 classical coins that are both heads or both tails with probability half. So they're correlated coin flips, and there's nothing quantum about this. We call this a it's just a mixture, a mixture of classical states. It just captures classical correlations. Okay. So now that we're able to talk about density matrices on multiple qubits, then we can start talking about things called the partial trace. So first, let's say you want to take the trace of a tensor product of density matrices, then the rule is this is just equal to the product of the traces of the individual ones. Okay. More interesting is something called the partial trace. So let's imagine that you had 2 qubits. Maybe they're entangled or classically correlated, and you have we call them qubits A and B, and we have a density matrix rho AB to describe the mixture of the system. But let's say you just wanted to talk about qubit A, right? I don't want to talk about the whole system AB. I just want to talk about A. Then the partial trace allows you to do that. It allows you to say, talk about the state of qubit A. And let me point out, this is another reason why the density matrix concept is needed, because before, when we just talked about unit vectors, we had no way of talking about just one part of an entangled state, right? For example, if A and B was in the pure state, the EPR pair, the 2 qubits together we can describe using this 4-dimensional vector. But actually, if you think about it, there was, this EPR pair is not the tensor product of 2 single qubit states. So what is the state of qubit A? Without density matrices, we don't have a good way of talking about it. But with density matrices, we can. And that's what this partial trace is. So we have this rho AB. And to talk about the density matrix on system A, we take the partial trace. So this subscript B means we're just going to discard system B, or people say tracing out or marginalizing over. So you remove system B, and you essentially take it out of, you just ignore it. So this is a 2 qubit density matrix that is in the input. And this is what you get as output is a 1 qubit density matrix. So what are the mechanics of this partial trace? Well, we can define it by its behavior on basis states, let's say, or just tensor products of vectors. So let's say that you had these 4 vectors. A1 and A2 are vectors, are states in the system A. B1 and B2 are states of system B. Then if we have this outer product, so this is not necessarily a density matrix, but it's some matrix in the tensor product space AB. So this is a when you take the partial trace, you're left with a matrix. Oh, sorry, I think I got this wrong. So let me cross this out. It's actually the other way around. We're discarding the system B, so this should be equal to the outer product between A1 and A2 times a number, which is the inner product between B2 and B1. So this is a number, and this is an outer product in the space A. And once we've defined the partial trace this way, then you can apply it to any matrix just by linearity. Because you can always write every matrix as a linear combination of these kinds of outer products. And you can equivalently define the partial trace over system A as well. It's like kind of the analogous thing. Okay, so now we have this very nice thing. No matter whether the state, the 2-qubit state is entangled or not, we can always have a meaningful way to say, here's the state of the system if we just restrict our attention to one part of it. Okay, here's an interesting fact. Let's say you have a mixed state on a system A. So maybe I should really just call it row A. It turns out that you can always view it as the result of taking a partial trace of some pure state on a larger system. So if we have system A and row A, it's some probabilistic mixture, there's always some external system B that purifies it. So there's some overall pure state, psi AB, this is a unit vector in this larger space, that if you take the partial trace of this unit vector in this way, you recover the original density matrix. This pure state psi is called the purification of rho, and they're not unique. There's many, many different purifications of any given density matrix rho. And these purifications are very important in cryptography because we can always imagine that if we have some, let's say you're one party in a protocol and that party has a density matrix, you can always model the system as ultimately being a pure state by just considering that there's some external system B that purifies the pure state, as the mixed state in the protocol. Okay, so just some quick examples. If we have, this density matrix rho, which is a tensor product of single qubit states 0 and plus. If we trace them out, let's say we trace out the B subsystem, then not surprisingly, we're left with the state rho, which is still a pure state. I mean, these are unentangled states. So you're just going to get the 0, 0 state out. Let's look at a more interesting example. What happens if you take the partial trace of the EPR pair, which is an entangled state? And I claim that no matter which qubit we trace out, we're going to get the maximally mixed state. Okay, so this is a calculation that I encourage you to try by yourself, right? One way to do it is you just expand out the EPR state in terms of the standard basis states. You take the outer products and then take the partial trace. And then you'll see that you get the maximally mixed state. So, so it says that, even though you're, entangled with someone with this EPR state, and, if you looked out at the two qubits together, it's in a pure state. When you just restrict yourself to one qubit, it just looks like a random coin flip. Okay. So let's talk about distinguishability of density matrices. If you have two density matrices of the same dimension, they're descriptions of possible states of a given system. We can measure how close they are by something called the trace distance. And you should kind of think about this as the quantum analog of the total variation distance. There's a mathematical technical definition of this trace distance, which is, if you're familiar with these things, it's the trace norm of the difference between these two matrices. So you take rho minus sigma, you get a matrix, you take the trace norm of it, and divide by 1/2. But actually, also an equivalent definition, which is very nice to think about, is that it has an operational meaning. The trace distance between any two density matrices represents the maximum probability of distinguishing between these two density matrices using any possible quantum operation. And here, just think of it as you can apply any quantum circuit you like. You measure, you apply unitaries to these two density matrices, and you want to distinguish them. What is the best possible probability? It's given by the trace distance. And since we're in I'm talking to cryptographers, this is an information theoretic quantity. So this is distinguishing with any size quantum circuit. Okay, there's some very, very nice properties of the trace distance that, when you're reasoning about, these density matrices, that will come very handy. So one thing is trace distance is always non-negative, and it's only 0 when you really have the same density matrix. It's, you can see from the definition that it's symmetric. Something that you'll use all the time is the triangle inequality. The trace distance between two states, rho and sigma, is at most the difference between rho and tau and sigma. It's convex. Okay, so that's kind of a nice property that you'll use in security proofs, for example. And these last two are also very useful. If you take, let's say you had, and this is very intuitive, let's say you had a density matrix on systems A and B, rho and sigma. And they had some certain amount of distinguishability, right? Maybe you can distinguish them with, say, I don't know, 50% probability. If you remove part of the system, you remove the B system, that cannot help you in distinguishing between them, right? So if you only consider how distinguishable are rho A and sigma B, it can only get worse. It cannot get better. So that's what this captures. And finally, the trace distance is invariant under unitaries. So you can apply the same unitary to both density matrices, does not change the distinguishability. And another reason to see that, way to see that is the unitaries are reversible. So if you apply to unitary, you can always just undo it and you get back to the original state. Okay. So there are nice properties that you should remember. Let's see, what did I want to, oh, okay, right. So here, I just want to illustrate one thing, which is we have density matrices on 2 qubits. And they're really classical density matrices in the sense that they're classical mixtures of classical states. So this is, you have 2 coin flips that are either both heads or both tails. That's the state described by rho. And the state described by sigma is that these coins are perfectly anti-correlated. So if one coin is heads, then the other coin is tails, and it occurs with half-half probability. So the trace distance between these two density matrices, if you consider both coins, oops, is going to be 1. Because if you're given both qubits or both bits, you can easily tell the difference between the two mixtures. So the distinguishing probability is 1. But of course, if you only look at just one of the bits, it just looks like a 50-50 coin flip. So your ability to distinguish between them is 0. So that's just a simple illustration of this. Okay, so for the very last part of this crash course, we're going to talk about some quantum complexity theory. All right, so this is familiar to a lot of you. This is a piece of the quantum of the complexity zoo. We have our favorite beasts, P, NP, P space. And how does quantum computation interact with them? Well, there's the quantum analog of polynomial time, which is called BQP, bounded error quantum polynomial time. And it certainly contains all of the problems that are classically solvable in polynomial time. So it contains P. We don't believe that BQP contains all of NP. We don't think quantum computers can solve NP problems in polynomial time. So these two sets should be different. There's a quantum version of NP, which is called QMA. So that's like the quantum analog of NP. It certainly contains BQP and it contains NP. And this QMA is contained in P space, right? Problems that can be solved using polynomial space. So this is to our best understanding, the picture of the complexity landscape when you put in quantum computation. Let me get a little more into what BQP and QMA are. So BQP is defined very similarly to the way that BPP, classical randomized computations are defined. So formally speaking, a language is in BQP. If there's some family of quantum circuits, one for every input length, this family has to be uniformly generated, meaning that there's a Turing machine, a classical Turing machine that you plug in the input length n, and then it will efficiently spit out the description of the nth circuit in this family, C sub n. And the size of this circuit has to be polynomial. Okay, and we have the usual soundness and completeness conditions. So for all instances x, if x is in L, then if you take the circuit C sub n and you plug in the input x, and you also initialize some other qubits to be the 0 state, you run your computation, and at the very end, you measure the output qubit that it accepts with probability 2/3. So this is a completeness condition. Whereas if x is not in L, then the circuit will reject output 0 with probability at least 2/3. Right? It does not accept x with high probability. These choices of 2/3 and 1/3 are somewhat arbitrary. You can, without loss of generality, assume that the completeness and soundness errors are exponentially small. So we can amplify and reduce the errors at an exponential rate with only polynomial overhead. Basically you just repeat the circuit polynomial number of times and you just take the majority, it turns out that this works, right? So there's no mystery there. Right, so that this class BQP satisfies a lot of the same nice properties as, say, BPP. You can amplify the errors to reduce the errors so that they're exponentially small. It's closed under complement. It's closed under composition. Things like that. So BQP captures polynomial time quantum computations. Oh, and I guess one thing, you might ask, well, what sort of gate set are we allowed? Well, you can fix a gate set. So let's say Clifford plus T. Right, so that's the gate set that we're working with. Okay, what do we know is in BQP? Well, this is a very interesting question. Certainly all problems in BPP, okay, if you can solve it with a randomized classical algorithm, you can solve it with a quantum algorithm. We know that problems like factoring and discrete logarithm are contained in BQP. And also, this is maybe the reason why quantum computing was studied in the first place, is we can simulate quantum systems efficiently in BQP. I won't say what simulating means, but this is of interest to like physicists and chemists. And we don't think that you can efficiently do so in BPP. Here's a canonical BQP complete promise problem. It's kind of like the one you would expect. You can call it Q circuit. It's just where if someone gives you a classical description of a quantum circuit C, and you ran C on the all zero input, tell me whether it accepts with probability at least 2/3 or at most 1/3. Okay. So this is, unsurprisingly, a BQP complete problem. Let me turn to QMA, which is the quantum analog of NP. Or, actually, it's even a better, a better way to put it is a quantum analog of the class MA. So QMA stands for Quantum Merlin Arthur. And, a language L is in QMA. If there's a family of verifier circuits, C1, C2, and so on, they're uniformly generated, they have polynomial size. What's a verifier circuit? It's exactly the same thing as a normal quantum circuit, except there's one register, there's a collection of qubits that are designated for what's called the quantum witness. It's just like in NP, you allow the verifier to take in some quantum, some proof string. A verifier circuit can take in a quantum proof, a quantum witness that it uses to verify whether an instance is in the language or not. So if X is in L, then there exists some quantum state psi, some quantum proof, where the circuit will accept X, psi, and also some of the qubits have to be set to 0, these ancilla qubits, and accepts it with probability 2/3. If X is not an L, then no matter what quantum witness psi you plug in, it will accept with probability at most 1/3. So very natural analog of NP. There's some probability of error. But again, we can reduce the error to exponentially small. I don't have it on the slides, but let me say there's something interesting about this error reduction. So a simple way to do this error reduction is, again, you can just repeat this verify circuit in parallel. So instead of asking for, but here's the thing. So remember this no cloning theorem that I mentioned, right? so how would you, naively try to repeat this circuit to amplify your probability of success, or reduce the error? So you can repeat it, but after you run one instance of this verifier circuit with the quantum proof state psi, you perform a measurement at the end. And remember that measurements, disturb the quantum state. So after you measure, you might not have this quantum proof state psi anymore, right? It might have collapsed into, say, some classical basis state. And then if you ran a second instance, tried to run a second instance of this verifier circuit C sub n, you wouldn't plug in the same exact proof state psi. This is unlike the NP case where you can just make as many copies of the proof as you want. So things get a little tricky here. So one way of doing it is you can say, well, instead of giving me one copy of the quantum witness, why don't you give me many copies? And then I'll just, for each instance of the verifier circuit, I'll plug in a new copy. I'll verify and then take the majority. So this turns out to work. You have to do some analysis to argue that the prover cannot cheat you by giving you, say, entangle the different witnesses together or give you different proofs. So that turns out to be fine. But you might be dissatisfied with the fact that now that your proof length has grown with the number of repetitions. And what's very interesting is you don't actually need to grow the proof size. So you can drive down the soundness and completeness errors to exponentially small using only one copy of the proof. And it's non-trivial to show this, but this uses something called Marriott-Watrous amplification. So you can actually amplify without increasing the proof size, which is very cool. And this is something that's actually used in later in the course, and let's say in the zero knowledge application. But it's something cool to keep in mind. So you can do this amplification just using one copy of the witness. Okay, so that's QMA. And the last thing I want to talk about is just a nice complete problem for QMA. So what problems are in QMA? Well, all problems in BQP, all problems in NP, and also something known as the local Hamiltonians problem, which is motivated by physics. Right? It's finding minimum energy states of quantum systems. You think of this as like the quantum analog of finding a satisfying assignment to a constraint satisfaction problem. Okay, so first, there's, again, a very canonical, straightforward QMA complete problem. This is we call Q-ver circuit. I give you a description of a verifier circuit C, and I want you to tell me if there is some quantum state psi that C would accept on with probability 2/3. Or for all states, they're accepted with probability at most 1/3, right? You want to distinguish between the two cases. So that's the canonical QMA complete problem. But the one that people like to study the most, and it's very interesting, is this local Hamiltonians problem. So let me describe this in a little more detail. So in this local Hamiltonians problems, there's a bunch of parameters. So there's K, A, alpha, beta. The input to the problem is a description of a bunch of measurements, H1 up to HM. And these measurements all act on n qubits. They refer to an n qubit system. So let's say we have these n qubits. But each of the measurements, HI, only act on K of them, a subset of K. So think of K as like 3, right? And in the back of your head, you should think of these H's as being kind of 3 set clauses, right? They're constraints on the qubits. Each of these measurements, they're projective measurements. They have 2 outcomes, either an accept outcome or a reject outcome. So that's the input. You're just given a bunch of these measurements. And you want to decide whether there's a quantum state psi such that, suppose that you measured psi with hi, and you say, what's the probability of rejection? So we call that pi. If you summed up all of these pi's, if it's at most this threshold alpha, we call that the yes case. And otherwise, if the sum of these probabilities, these rejection probabilities is at least beta, then we say that that's no case. So of course, we need alpha to be less than beta. Right? So for simplicity, imagine that alpha is 0. So that in the yes case, there's a state that is never rejected by any of these measurements. But in the no case, then with some noticeable probability, one of these measurements will reject this state. So this is the you can kind of think about this as like the quantum analog of 3-sat. All right, so that's the local Hamiltonians problem. And it turns out that this problem is QMA complete for k equals to 3. And beta and alpha can be anything as long as they're separated by an inverse polynomial. And so it's QMA complete. So that means I can transform any instance of this Q-verse circuit problem. So I have a verifier circuit. I can transform it into this instance of the local Hamiltonians problem, right? I have these collections of the measurements such that if we were in the yes case for this verifier circuit, meaning that there is a quantum proof that is accepted with high probability, then in the yes, then we're in the yes case for the local Hamiltonians problems. But we also map the no case to the no case. The interesting thing to know about this is there is a direct mapping from, proof states theta that are accepted by this verifier circuit to states psi that are accepted by these local measurements. So let's say that psi is a quantum state that's accepted by this verifier circuit. Let's imagine that it's accepted with very, very, very high probability, exponentially close to 1. Then the corresponding state psi that's accepted by these 3 local measurements will be something that's called a history state. And this history state is like the quantum version of the Cook-Levin tableau. It kind of has a snapshot of the intermediate states of each of these of this verifier circuit. So it's a uniform superposition over all time steps of this verifier circuit. The initial snapshot, the size of 0, is going to be the input theta into the circuit. And then for every time step afterwards, we just evolve it by applying one gate at a time from the circuit. So G sub t is the tth gate from this circuit. And we just apply it. And we take this superposition. We have a register that keeps track of the time step that we're in. This is called the history state. And it turns out that if theta is accepted with very high probability, then this history state will be also accepted with very high probability by these local measurements. Okay, and yeah, so that's it. Thank you very much for braving these 3 hours. I know it was a whirlwind, but hopefully now you're primed for the rest of the workshop. So thank you very much.